Chapter 11, Kinetic Theory of Gases, Section 11.6, Mass Transport and Thermal Conduction. Diffusion and effusion are two types of mass transport processes. Effusion is the process in which gas particles pass through a tiny hole of a container. Gas effusion can be used to produce a beam of gas particles. For example, molecular beams. The effusion rate is proportional to the average speed of the gas particles and also the size of the hole. Let's watch a video on effusion.
Effusion is the process of gaseous atoms flowing into a vacuum through a hole in a container.
As you can see, if the gas particles move faster, we'll have a higher effusion rate. And also, if the size of the hole is slightly larger, that means, well, it's easier for those particles to pass through, and we'll also have a higher effusion rate. Now let's talk about diffusion. Diffusion is the process by which particle density evolves in response to a spatial gradient in concentration. Well, let's look at this diagram. Over here we have only one particle. At first there was a partition. This particle can only move in this area. If we remove the partition, this particle can reach to the other area here. Now let's look at a bunch of particles. Again, at the beginning we have a partition over here. We have all those particles in the left side area, and then after we remove the partition, the particles can occupy the entire space. And this is actually diffusion, because at the beginning we have a high concentration on the left, a zero concentration on the right, and just due to the random motions of the gas particles, eventually they will occupy the entire container. The concentration will be homogeneous in the end. And over here we see a kind of more continuous spectrum of the number density. At the beginning we have a high density on the left, and gradually it diffuses to the right. In the end, the color is homogeneous, and that's a so-called equilibrium regarding the concentrations. The diffusion rate is also proportional to the average speed of the molecules, so if they move faster, they can occupy the entire container first. And also it's proportional to the concentration gradient. So what does that mean? So if there's a zero concentration gradient, like right now, okay, there's no more diffusion. The net diffusion rate is going to be zero. If you have a container with a homogeneous concentration inside. Now let's watch a video on the diffusion of ammonia and also HCl. So you can see over here in this picture, ammonia travels a longer distance than HCl. And why is that? Well, the molar mass of ammonia is 17. The molar mass of HCl is about 36.5. So ammonia has a much smaller molar mass and therefore higher average speed. The average speed is proportional to the square roots of 1 over m, where m is the mass of the gas particle. So since ammonia is much lighter than HCl, it travels faster than HCl. Now let's watch the video. So over here you see ammonia and HCl diffuse.
Diffusion is the process whereby molecules of gas move to completely occupy a space, giving a uniform partial pressure. In this example, gaseous ammonia and hydrogen chloride diffuse through air from either end of a sealed tube. When the two
they form ammonium chloride over here. So by doing this experiments, we can actually just measure the ratio between the average speed of ammonia and the average speed of HCl. So it's going to be just this distance divided by this distance. And that's one way to study the kinetic theory of gases. The diffusion rate is proportional to the concentration gradient and also the average speed of the molecules. So we will study the diffusion rate and how it depends on the concentration gradient and average speed more quantitatively on this slide. Assuming a gas diffuses in the x direction, so this is going to be x, and we're going to see some net diffusion from left to right. At the end, we should have a homogeneous concentration distribution like this. Alright, but at first, let's assume we have a concentration gradient, we have a lower concentration on the left, we have a higher concentration on the right. Let's derive the net diffusion rate at the position x. We will just examine the flow rate of the gas particles in the forward direction and also in the backward direction, and we'll take the difference. That's going to be the diffusion rate. We'll assume the number density at position x is rho. So over here, the number density is rho. And we're going to assume the gradient of the number density is a constant. We're going to use g for that gradient, which is d rho over dx. And therefore, the number density at over here, x minus dx, it's going to be rho minus g dx. The number density at x plus dx is going to be rho plus g dx. Alright, so we have different density on the left and on the right. Okay, over here, this graph is a bit exaggeration. Alright, so you can see the density here is much smaller than the density here. The average number density between x minus dx and x, so between here and here, I'm going to take the average. So it's going to be rho here and rho minus g dx here, so I'm going to take the average. On average, the density here is rho minus g dx over 2. What about the average density over here? Again, I'm going to take the average between over here, it's rho, over here it's rho plus g dx. The average is rho plus g dx over 2. So we have a concentration gradient. The concentration on the left is lower than on the right. On the left, the average is rho minus g dx over 2. On the right, it's rho plus g dx over 2. And then we can compute the number of particles between x minus dx and x. Well, it's just the number density multiplied by the volume. The volume is just the this distance multiplied by the surface area. I'm going to just use A here. Don't worry about the value of A. It's going to be the same for the left side and for the right side. Eventually, they will just cancel. So we have this number of particles on the left. Similarly, we have the number of particles on the right. These two have the almost the same expression, except we have a minus here and a plus here. For simplicity, we're going to assume half of the molecules moving forward, half moving backward, or at an average speed v. So within a time interval, dt as dx over v, then the number of particles moving forward and crossing x is this much. So it's going to be 1/2. It's just because we're going to assume just 1/2 of the particles are moving forward and cross the midpoint. Alright, just 1/2. This is just the volume of the left side, and this is the number density of the left side. The number of particles moving backward and crossing the midpoint is 1/2. times the volume of the right side times the number density of the right side. So we have this number of particles that move forward and backward and cross the midpoint. So I want to show you the diagram again. So we have half of the molecules moving forward and passing the midpoint. Also, we have the expression for the number of particles moving backward and cross the midpoint. Alright, now the overall particle flow rate due to the concentration gradient, well, it's gonna be this. This is moving forward, this is moving backward, and then we have over here, this is just the time interval, and we're gonna divide everything by the unit volume. So we have this so-called overall particle flow rate due to the concentration gradient per unit volume. Alright, so we have this fairly complicated equation, but on top, this is the number of particles moving forward minus the number of particles moving backward. Alright, just so that we have a net flow rate. Okay, this is just the time interval, and over here it's just we just want to know what's the flow rate per unit volume. And now we have equations to simplify. I see ADX, ADX, ADX. Let's cancel all of them. We have time interval on the bottom. We just copy that. And then we have something over here. DX, 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 they cancel. And also rho and rho cancel. And then in the end, we get negative GV over 2. Alright, G is the gradient of the number density. So you can see this diffusion rate is proportional to the gradient. And V is the average speed. Now you can see the diffusion rate is also proportional to V. Why do we have a negative sign? Well, it's just because the direction of the flow is from higher concentration area to the lower concentration area. Alright, that's why we have a negative sign over there. So this gradient is positive from lower concentrated region to a higher concentrated region, but the diffusion is from higher concentration to lower concentration. Although this derivation, this entire derivation is not really rigorous, but at least we just proved semi-quantitatively that the diffusion rate is proportional to the concentration gradient, and also proportional to the average speed of the gas particles. For comparison, the diffusion rate mainly depends on 1. The speed of the particles, and 2. The size of the aperture through which the gas particles pass. Now let's look at thermal conduction. Thermal conduction and the diffusion of gas particles are similar, and they are both considered energy dispersal processes, and they both increase the entropy of the universe. As the diffusion rate is proportional to the concentration gradient, the thermal conduction or heat transfer rate is proportional to the temperature gradient. Of course, if the temperature is the same everywhere, there's no more thermal conduction. As the diffusion rate is proportional to the average speed of the gas particles, that is how fast the particles move, the thermal conduction rate depends on the thermal conductivity of the material. So that means how fast the thermal energy can be transferred. Usually metals have higher thermal conductivity than non-metal. In essence, thermal conduction results in the redistribution of the thermal energy of particles, while diffusion results in the redistribution of the positions of the particles. As the positions of the particles are redistributed in diffusion, the energy possessed by those particles are consequently redistributed. Therefore, it's also considered as energy dispersal. So both diffusion and thermal conduction involve energy dispersal. That means energy always flows spontaneously from a high energy density area to a low energy density area. This is dictated by the second law of thermodynamics. Over here, there's animation of thermal conduction. We have a high temperature region and low temperature region, and you can see heat is transferred from left to right.